Hello, this is Phil Ramsey, and this is a follow-on discussion to the DOE training. And in this section, I'm going to talk about a new technique for analyzing designed experiments and building predictive models called fractionally weighted bootstrapping with auto-validation. Okay. So we're going to talk about what we mean by auto-validation and fractionally weighted bootstrapping. Going to give some examples of it. It does require Jump Pro, and I'll return and discuss the pDNA case study. This method, what we call fractionally weighted bootstrapping and auto-validation, was originally a joint collaboration between myself and Dr. Chris Galtwalt, who's the head of statistical research for Jump. And the original motivation was to find a way to expand the use of machine learning and predictive modeling in small data sets and more specifically designed experiments. So basically you do a designed experiment. They're typically efficient in the number of trials and data collected. And also because of that, there's a problem trying to build a predictive model. Remember, in predictive models, we typically need some form of validation to determine what model actually predicts best. So when you have big data, machine learning methods are typically focused on big data. It's relatively simple. You can take some of the data, hold it back, sometimes called hold back cross-validation, fit models and validate them on the other data. In designed experiments, this is not possible. So how do we come up with some measure of prediction error or validation error? And this has historically been a problem because the designs are so efficient, okay, that we can't hold back any data and use it for validation. In fact, if we were to remove any data, we would destroy the structure of the design, and that could have serious ramifications for our ability to fit models. So what people often do is they use a surrogate measure of fitting error that referred to as particularly the AIC, Akaiiki information criterion. We've discussed this in the past, and it acts as a surrogate to try to estimate how well the model might predict. But we find in practice the AIC in general is just not a satisfactory approach for coming up with what is the true prediction capability of a model. You really need some form of validation. Well, one thing we could try to do, and this is a simple example, we have a set of data, really simple little design, and we collect a response. Well, what if we took the same data, duplicated it, and we're going to call it the training and validation data? Well, that's not going to really work very well, because what that'll do is, since the validation set is the same as the training set, we're always going to fit the largest model possible, no matter how well the model might actually predict in practice. Okay. So if you look at what we call cross-validation, and we have talked about it, again, you have a training set of data, you fit the model on it, and then you have another set called the validation set, and you test the model. You see how well it predicts on the validation data. And you can think of this, believe it or not, as a weighting scheme. So if it's the training data has a weight of 1, and the validation set 0. In other words, if you take the weights and multiply them times the y's, in other words, just multiply these two columns together, the validation data is zeroed out. Likewise, if you want to do validation, take the validation weights, multiply them times y, and you zero out the training data and you can look at just validation. So basically the idea is we use the training data, okay, which is the first 8 observations, to fit models. And then we use the last 8 observations to evaluate the models. In other words, we use data we didn't use to fit the model. People don't realize that this is really a weighting scheme, and the weights are simply 0 or 1. If it's in the training set, it's a 1. If it's in the validation set, it's a 0. Okay. So what we decided is, why couldn't we generalize this idea of weighting? Okay. So in our scheme, we're going to use the same data for training and validation, but we're going to create a set of weights. And these are non-integer weights, they're fractional weights, such that we're going to drive what we call anti-correlation. In other words, we're going to drive the training set and validation set to be different. No observations or data are ever removed. Because we need all the data. So we're going to use this weighting scheme to use the same data for training and validation. And we started out calling this the auto-validation method, since it self-validates. And the key to it is to understand this fractional weighting scheme. Today, I will not get into deep details about it. I'll just illustrate it to you. So again, you assign a set of random weights, and they're fractional, to the training data. And then you take a copy of the training data, we'll call it the auto-validation set. So every observation in the training set has a corresponding observation in the validation set. But the way we do the weighting, if any observation in the training set has a big weight, it's given the corresponding observation in the validation set gets a low weight, and vice versa. So we refer to this as fractional weighting. So we have a set of weights, and we can show the weighting causes the training copy and the auto-validation copy to be anti-correlated. In other words, we're driving them to be different with a weighting scheme. And what's nice about this, we could repeat this weighting scheme thousands of times, just generating new sets of weights at random. And on each set we generate, we could fit a model. And we refer to this procedure as fractionally weighted bootstrapping. Bootstrapping is an old, what we call resampling technique. And this is actually a twist on it. So that is our strategy. We're going to use a weighting scheme. We're going to use the original training data as also auto-validation data, use this weighting scheme, fit a model using auto-validation error to pick the model. Then we're going to create new weights at random, repeat the process, and do this thousands of times. And again, we call it fractionally weighted bootstrapping with auto-validation. Okay. So what do we do with the results? So here's an example. This is really simple. I have this simple model, just 3 main effects and 3 two-way interactions. I did thousands of iterations of modeling, and you can use all types of modeling like forward selection. This is a very general procedure. It's up to you what method you want to use. And then I did it thousands of times, and I tracked the proportions of times terms got in the model. How many times did terms get picked by the model fitting strategy when I did it thousands of times? Traditional modeling, predictive modeling, usually they make one pass through the data with an algorithm. As you get used to fractionally weighted bootstrapping and see how it works, you realize that's in general not a good idea. These algorithms can have their own idiosyncrasies by making thousands of passes using this random weighting scheme, you gain a lot more information. So notice X1 got in the model 97% of the time, X2 74%, and so forth. And then we had a couple of two-way interactions that rarely got in the model. The question is, are these last two interactions, do we want them in the model? Well, how do we make a decision on that? In other words, how do we calibrate our results to get some idea of how often or how important are the inclusion rates for predictors, potential predictors, and how do we decide some may not be important? Well, one way to do it is we add yet another twist to fractionally weighted bootstrapping. We incorporate what's called a null factor or pseudo factor. All it is, in this case, is just a random normal set of numbers. It's completely random and it has no relationship to the response whatsoever. And we track how often it gets in the model. So here's an example, same model, same data, and we incorporated a null factor, and the null factor got into the models 25% of the time. That would lead us to believe that the X2, X3, and X1, X3 interactions are really not important to prediction because they got into the model less than the null factor. So the null factor, it's optional, by the way. You don't have to use it. It's a way of calibrating what potential predictors seem to be the most important. Okay. So again, we're going to give an illustration of how to do fractionally weighted bootstrapping. Again, you need Jump Pro. Later I'll show you a Predictum Add-In that actually automates a lot of this. There is also a Jump Add-in that will set up the data table for you. It won't do the analysis. The Predictum app will actually do the whole thing for you. So you can get this add-in, it'll set the table up for you. So I'm going to illustrate. I'm going to open up the pDNA data I've shown you before. Okay, so here's the data. Again, 5 factors, 15 runs, definitive screening design. Okay, and under add-ins, so I've installed an add-in. This is a general one you can get on Jump Communities. And say auto validation setup. Notice what it did. Okay. It took the original data, appended a copy, and then assigned a weighting scheme. Again, we're not going to get into details on weights, but the way this has been set up is it's a weighting scheme such that bigger weights in one data set, for instance, this is probably a good one, X3, the weight is 3.7, so this would be 1, 2, 3. And then it assigns the weight. Did I go to? I went too far, 18. So it goes, the training set is a 3, and the validation set, it's a 0.7. Okay. And then it automatically generates a null factor. Again, I won't get into the details of the weight formula. It's a bit complicated. It's actually some rather dense written Jump scripting language, but the add-in contains the formula. So now I want to fit models. So how would I do this? Well, I'm going to fit these again, augmented full quadratic models. I'm not going to do a whole analysis. This could take too long. Okay, so pDNA is the response. We know there's a validation set. And this is important. You have to tell Jump where the weights are stored. So Jump is going to go to the weight column on each iteration of the procedure and multiply the fractional weights times the responses. That's the key to what we're doing here. So I'm going to go to Generalize Regression. And I'll pick a simple method here so this can go very quickly for you. So I click forward selection. So notice it's going to use the auto validation set to pick models. And I click go. Okay. So it picks a model. One pass through the algorithm, it picked a model. Okay. And it based it on validation error. Okay. That's how it picked the model. I'm going to come over to the table of estimated predictors in the original scale, right-click in the estimates column, and there's this nice function in Jump Pro called Simulate. So I want to do a series of simulations, and it's asking me on each run of the simulation, are there columns that you want to swap out? So what I want to do is take the current column of weights and replace it with a new. It'll generate a new column of weights. And I'm only going to do this 100 times just to illustrate for you what's going on. Okay. So click OK. Okay. So obviously in real time I can't do a big problem. I recommend doing this at least 2,500 times. So what it did is on each run, it fit a model. If a term did not get in the model, it gets a 0. Okay, so that's what its coefficient is. It's a 0. And you include, follow this up for you. You see, you can get percentages for all of the factors. Okay, so if you went to the distribution platform, okay, I could put in all the potential terms. Okay. And this is what is neat in Jump. See the summary statistics report? I'm going to hold down the control key, click on one of them, and I want to customize the report. I'm going to deselect everything, and I'm going to select proportion non-zero. Okay. So I have all these proportions. Again, I didn't do this nearly long enough to fully explain the method. Now I'm going to right-click on one of these modified summary statistics reports and say make into a combined data table. So here we have it. Here's a table of all the factors and how often they got in the model. Okay. And again, I didn't run this long enough for this to be very meaningful, but you could go through this and get an idea how often certain terms entered the model, giving you some idea of what factors might be important. Okay, I'm going to close that. And notice something else I received were coefficient estimates. Okay. In other words, I've gotten various coefficient estimates for each potential model term. Again, if it didn't get in the model, it's 0. And what I can do is take an average of these model coefficient values, model averaging, which we've seen it before, but this takes it to a new level. And with that model averaging, create a new formula. Okay. So if I do this thousands of times, I create averages for each model term based on thousands of model fits. And in each fit, again, we generate a new set of weights, which gives an approximation to what would happen if you could run the same experiment 1,000 times, 1,000 replicates of the same experiment. Bootstrapping is a much researched and common method used to mimic resampling or mimic sampling large numbers of times from a system. So it's on very sound ground. It's well known and its properties are well understood and it's well accepted. Okay, so I'm going to close all of this out. This gives you the idea of how the method works. So I'm going to close out these data tables. Okay. And now I'm going to go to the Predictum. Let me move ahead in the slides first here. So this steps you through what I just did. Shows you how to do it. Okay. By the way, here's one. This is a bigger problem. I can't do this live. It takes too long. But these are a Pareto diagram of the proportion non-zero. There's the null factor. So notice all of the factors to the left of the null factor got into the model more than a null factor. So maybe we want them in our model. Okay? And maybe the ones to the right we don't really need. If we do model averaging, we don't even have to worry about this because we're not going to do model reduction. Again, fractionally weighted bootstrapping is a very general procedure that can be used with literally any type of modeling interface. So we use it with GenReg. It can be used with neural networks, many other types of modeling. Okay. So what I'm going to do now is go back to my data set and show you the Predictum Add-In. So this is an add-in you have to get from Predictum. And it's going to do fractionally weighted bootstrapping with auto-validation, but then it's automatically going to generate model averages. Okay. So we start in a similar fashion. To speed things up, I'm just going to define a full quadratic model. So I use the response surface macro. Response is pDNA of titer. Okay. So there it's told me which is validation, which is training, and it's put the weight column has been identified in the frequency box. Run. Again, to speed this up, I'll use forward selection. Okay, and it says do 1,000 simulations. And again, I like to do at least 2,500. I'm going to do 200 just to illustrate what it does. Okay, and this will go pretty quickly. Notice what it did. One, it generated the so-called Pareto plot, which is not really the key output, but down here, it generated model average estimates. And these are weighted average estimates. They're weighted by these root average square error weights I talked about in 2 sessions ago. And we don't need to get into the details of them. So what do we do with this? Well, here's what's nice about it. I can actually create a prediction formula. So JMP has done all the averaging. It creates a prediction formula for me. Okay. And it's what the formula looks like. And here's what I recommend. Since you have JMP Pro, these are actually big, somewhat unwieldy formulas. I recommend you publish them to a formula depot. The formula depot actually condenses them down and puts them in a much simpler form. So open up the formula editor in the formula column, right click and say publish to formula depot. So it opened the formula depot and stored the formula. Okay, so I'm going to close that. So what I'm going to do, believe it or not, I'm actually going to close this. I don't need it. Okay. And I'm going to open up the combined data. Okay, so here's the combined data. And what you can do, okay, if you have a formula depot available, you can actually deploy the formula from the formula depot. So if I look through these formulas, I was actually showing you this earlier as an example. Okay, I see what it wants to do. It wants to encrypt the formula. Okay. So we take a look at the formula. So this formula was created in that auto validation version of the data. I saved the formula to a jump formula depot. And then once you have a formula depot open, all you have to do is run a script. And I showed you how formula depots work, and it'll deploy it to any data table you want. So this formula was created in another data set, stored in a formula depot, which you can save as a permanent record, and then I deployed it to this data set. And again, we now have these prediction formulas, so we can do things like, again, I'm going to just use the validation data. So I'm going to use my row states. And we can do things as we showed earlier, such as using the profiler. And by the way, this model created by the Predictum Add-In worked really well. Very good prediction error. So we deploy it. And of course, I've shown this before. And then we optimize. So the key to this is, okay, is that we began by fitting a fairly complex model, and there's a lot of evidence that this data is very nonlinear and interactive, and you really need those more complex models. And then at this point, you know, we could go ahead and then we could use a simulator and, you know, do further simulation studies. Again, you know, if you call up the simulator, and it's automatically put in some standard deviations, but in reality, you'd want to use your own. And then, as I've said before, I consider assessing variable importance to be quite useful. And it's making no mistake about it, one better control feed rate very, very closely. It's critical to the process. Okay. So that's basically how the method works. Under the hood, there's a lot going on with this approach. So I can't show you every bit of it, and some of it takes time, but the Predictum Add-In really makes it relatively painless to generate some powerful predictive models, store them in a container called a jump formula depot, and then deploy them as appropriate to new data sets where it makes sense. In other words, the formula would make sense for the new data. Okay. So I'm going to go back to the slides. Okay. So I've just illustrated how the method works. Okay. So this was a long drawn out process. Again, I won't show the time, but given you're doing this with your actual data, I mean, it's fine if you do something that's going to take a while for the full computation to occur. And this is the key. You're given these model averaged coefficients. Okay, and there's the model. And then I mentioned publish to a formula depot because it's going to simplify it for you, make it much easier to use and to deploy. And then once you have the formula depot, if you have in the formula depot, you can use the option run script, and it'll ask you what table you wanted to deploy the formula to, and it will do so. You know, by the way, in the current version, you do need, in the target data table, you need to create a null factor column and assign it zeros. In other words, we want to null it out. We don't need it. There's a new version coming out where this will actually go away, but here's the formula, and it's easily deployed to the data table. Okay. And how did we do? We showed this earlier in the DSD discussion, and I apply the data. There's the model on the training set. It nicely doesn't look overfit. And there's it's deployed to the CCD data, which I've pointed out in the past was a challenge because that CCD was done at a different time, different operators, different batches of raw materials, different fermenters. It's amazing how well this predictive model actually holds up. Okay. So what do we conclude? Well, traditionally building predictive models from designed experiments has been limited by, in fact, the use of machine learning, limited by the lack of validation trials. They just don't exist. Traditional surrogates like AIC simply aren't that effective. In fact, with DOE data, you'll find they're very ambiguous in many cases. Those actually were those surrogates designed for much bigger problems than you see in DOE. So using the auto-validation method combined with the fractionally weighted bootstrapping to mimic thousands of repetitions of the experiment, we can build even very large models. In our case, we built a huge supersaturated model. Okay. And then we can apply those models in practice. So we consider auto-validation and fractionally weighted bootstrapping in the future to be a standard part of DOE analysis where the goal is prediction, and we find almost all the time when you deal with scientists and engineers, ultimately they're after prediction. If you can't predict, then you don't truly understand. Okay. And this is actually what's nice about this. This is a completely empirical approach, makes few assumptions, so we don't really care, honestly, what the distribution of the response is. That information is never used. The null factor can be used, it's up to you, as a calibration device to see which terms might be most important. And it does free us from explanatory modeling techniques like using p-values, R-squared, or the surrogates AIC and BIC, which typically have their own set of problems. And this method in general, I may have mentioned, has been by my PhD student who's finishing his dissertation, has thoroughly investigated this approach under many challenging conditions, and this method clearly outperforms in terms of prediction error traditional approaches. In fact, it's not even close, and a paper is in the offing for a peer-reviewed publication, which is going to explain all of this and show the results. And I think people are going to be very convinced that this is the way to go for building predictive models from DOE. By the way, it works perfectly fine with observational data. So I know some of you, if you like working in gene and cell therapy, you don't have a lot of data anyway, but if you have some observational data, this method works perfectly fine. Like all the modeling techniques in JUMP, it's totally agnostic about the source of the data. So fractionally weighted bootstrapping and auto-validation actually don't care if it's a designed experiment. Okay? And they seem to work extremely well. And we have a lot of evidence to back that up. Okay. Okay. And I keep saying this, I highly recommend model averaging for predictive modeling. And there's actually some really nice papers that have been written over the years recommending it. It just hasn't gotten the attention it really deserves. But with the rise of machine learning and data science, people are learning that these so-called ensemble methods are very powerful. So the Predictum Add-In is designed to do model averaging and fractionally weighted bootstrapping. So it does both for you. And there's some references if you're interested. So that concludes the discussion of fractionally weighted bootstrapping and auto-validation, which I do indeed consider a very important tool in the scientists and engineers statistical toolbox.